live experience. Really appreciate
Good afternoon, everybody, and welcome to the Soil Science Seminar today. Actually, Soil Science Seminars. We're going to have two presentations. The first speaker is Tong, and Ting is a PhD student at Nanjing University of Information Science and Technology in China. He's visiting Iowa State University, and he's going to be here for a few more months before he returns back to China. He's a delightful guy, so if you haven't had a chance to get to talk with him or know him, please do that sometime this summer. Today, Bing is going to talk to us about some of his work measuring soil thermal properties. Now, I forgot to say, he's a meteorology student. So he and his professor realized the importance of soil in exchange with the above ground, with the atmosphere. So he really wants to study more on soil properties so that he can engage in some of this meteorology work. Please welcome Bing Tong.
Thank you, Dr. Horton. Thank you for your introduction. Hello, everyone. I'm so glad that I have the opportunity to share my work with you. Today, I will present soil thermal property values as functions of water content and bulk density. First, we should know why we must study soil thermal properties. Soil thermal properties include volumetric heat capacity, thermal diffusivity, and thermal conductivity. They impact soil temperature and heat transfer. The soil thermal properties play an important role in heat and mass transfer between land and atmosphere. So yeah, it's important to study soil thermal properties. Then, how can we quantify soil thermal properties? What soil properties impact soil thermal properties? The magnitude of soil thermal properties depend largely on soil parameters such as water content, bulk density, texture, and mineral compositions. And much effort have been made to develop empiric models based on selected soil parameters. Among these parameters, soil water content is the one that varies most under field conditions, and it has received a lot of attention. And soil bulk density can also change with time. Tilled loosens soil, and shrink swell processes can change soil density and arrangement with wetting and drying cycles, such as drought and storm events. Freeze thaw processes. When water freezes, it expands about 9%. So as water in moist soil freezes, it produces pressure. It produces pressure in soil cores. So the cumulative effect of freeze-thaw cycles and disruptions of aggregates can cause expansion, cracking, and crumbling of the soil. However, in most hydrologic studies, the dynamic soil bulk density is assumed to be static. In fact, that is not true, and the influence of this assumption is not known fully and may be important. Even though we know that the relationships of soil thermal properties with water content and bulk density are important, few studies have reported how soil thermal properties vary with water content and bulk density. So the objective of this study is to investigate how thermal properties of a tilled field soil vary with water content and bulk density. Materials and methods. A field located near Ames was used in this study. The field was tiered to a depth of 20 centimeters, and the soil and then kept barren. Undisturbed soil cores were connected immediately after tillage and after subsequent rainfall. Metal cinders, 80 centimeter internal diameter and 5 centimeter height, and 7.6 centimeter diameter and 7.5 centimeter height were used for soil sampling, and the shorter one were used for the 0 to 5 centimeter, 5 to 10 centimeter, 10 to 15 centimeter soil layers, and the longer one were used for the 15 to 22 centimeter and 22 to 30 centimeter soil layers. The soil samples were connected 6 times during the summer of 2015, from May 22nd to September 5th. And 4 soil cores were connected at each soil layers above 22 centimeter at each soil sampling time. So in total, we have connected more than 80 soil cores. In the lab, the soil was saturated in a vacuum chamber from the bottom for about 12 hours, and the saturated soil cores were weighed and its volume recorded. After that, it was transferred to a pressure cell and drained. The drained water was weighed, and then the soil core was oven dried at 105 degrees Celsius, and the oven dried soil sample was weighed. So, based on this measurement, the bulk density and the water content can be obtained. For the soil thermal properties, they were measured with a KD2 probe heat pulse sensor in a temperature-controlled room, and the SH1 sensor connect to KD2 probe consists of 2 needles. Each needle has 1.3 internal diameter and 3 centimeter long, and separated by 6 millimeters. And one needle contains the heater, another one is the temperature sensors. With the sensor inserted vertically in a soil core, a heat pulse was applied to the heater, and 60 temperature at the temperature sensor were recorded. All the 3 soil thermal properties were derived from the temperature response curves. For each soil course, it was measured 3 times at the saturated, unsaturated, and oven dry water conditions respectively, and each measurement lasted for 2 minutes, and 15 minutes of sensor soil equilibration time was used between each measurement. So for each soil course, we have 1 bulk density, 3 water content, and 3 thermal properties responding to each water content. In this study, the various model was used to describe the volumetric heat capacity. It is the sum of volumetric heat capacity of water and solid. It's a linear equation. In this equation, the Cs is the specific heat capacity of solid. It was measured. And Cw is the volumetric heat capacity of water. It's known. And Lu 2014 presents an empirical equation relating soil thermal conductivity to water content, bulk density, and soil texture. It's an exponential equation. Here, the number dry is the dry thermal conductivity estimated by soil porosity. And the alpha and beta are shape factors that can be estimated by the soil particle size information and the bulk density. Here, the alphas, the FCL and FSA are the USDA fractions of clay and sandy, respectively. The soil thermal diffusivity is determined as the ratio of thermal conductivity to volumetric heat capacity. Results. The figure shows figure 1 temporary dynamic of bulk density. It shows the average bulk density for 10 to 15 soil layer and the daily rainfall. For the whole soil layer from 0 to 30, the bulk density ranged from 0.9 to 1.5 gram per cubic centimeter. And we can see the dynamic of bulk density can be divided into two stages. One is the rapid increase stage, another one is the relative small increase or stable stage. And our findings are consistent with the earlier reports that under conventional tillage, the bulk density of soil layer increased in the first few weeks, and the bulk density of after tillage are the combined effect of gravity and wetting drying processes. Figure 2. It has 3 sections, and each section shows the selected soil thermal property varied with water content for soil cores at different bulk density values. And the x-axis is water content, the y-axis is the thermal properties, and each point is the average values of actual triplicate measurements made on soil cores at given water content. And the solid curve indicate the curve trend by fitting. And the form of the fitting equation for volumetric heat capacity and for thermal conductivity are from the soil thermal property models mentioned before. So for the volumetric heat capacity, it increases linearly with water content. For the two bulk density values, the volumetric heat capacity versus water content are almost parallel. For the thermal diffusivity, it increased dramatically with water content at relative small water content volumes, and increased gradually at intermediate water content and decreased at the relative large water content. For the last one, the thermal conductivity, it increased sharply with water content at relative small water content values and increased slowly as water content increased. Such trends of soil thermal properties with water content have been reported earlier, but the figure also shows that the increase in bulk density will lead to increases in all of the soil thermal properties. That's our finding. This figure shows soil thermal properties varied with bulk density over a range of water content. And the x-axis is the bulk density. The y-axis is the thermal properties. And the different markers represent the soil thermal properties measured at different water conditions. And for this thermal diffusivity and thermal conductivity, we can see that as the bulk density increased, the thermal diffusivity and thermal conductivity increased. For the volumetric heat capacity, it increased as bulk density increased at oven dry and partially saturate water conditions, while it decreased as bulk density increased at saturate water condition. The reason for the saturate volume heat capacity decreased is that the saturate water content decreased as the bulk density increased, and the soil have larger volumetric heat capacity than solid. And the range of soil thermal properties measured at the partially saturated were larger than that made at oven dry and saturate water conditions. It indicated that the bulk density impact thermal properties most at partially saturation. To show how soil thermal properties varied with water content and bulk density, some 3D graphs were made. And this graph, the divarious mode was used to graph the volumetric heat capacity surface. The Lu 2014 model was used for the thermal conductivity surface. And the surface of thermal diffusivity was estimated as the ratio of estimated volumetric heat as the ratio of thermal conductivity to volumetric heat capacity. So this figure shows how the measured and estimated soil thermal property values varied with water content and bulk density. Because the data were connected over a range of water content and a range of bulk density, so they did not prevent a curve. Instead, they prevent a surface function. And this result represents our actual field condition over time. So thermal properties not only varied with water content, but also varied with bulk density. And this figures also displays the performance of the selected soil thermal property models. And generally, the estimate soil thermal properties value agreed well with the measured values, and the relative difference was within 12%. Conclusions: the bulk density of the tilled field did not remain constant during subsequent wetting and drying cycles. Soil thermal properties were not only affected by water content, but also by the dynamic bulk density. The dynamic bulk density should be included in heat and mass transfer models. This study was supported by this agency, and I want to thank my co-authors and my colleagues who helped me for the studies. Thanks for attention. Question?
We have time for about one question or so.
Dr. Hammack.
Do you have a physical explanation or conceptual model for how the bulk density increased? Why did the bulk density increase over time? How would you explain it?
Okay. So the field was tilted that then with time, the soil will compact it, and after the rainfall, it also will help to compact the soil. So that's why bulk density increased in the field. Doctor?
In the laboratory experiment, you started out with a saturated. You started out saturating the core,
Yeah.
and then you let it dry. So in that, when you dried it from saturated to partially saturated, was each core set at the same pressure potential? Was the pressure potential constant, or was it just dried to the water holding capacity of the soil? That's my first question. And the second one is, at that point, did you assume the bulk density would be the same for the core as it was in the saturated state?
Okay. So Dr. Thompson, first question is how I dry the soil. The first question. Yeah. After saturate, we transfer the soil into a pressure cell and then applied the same pressure at minus 50 kPa. Yeah, and open dry it. Yeah, the second question is that is the bulk density is the same at the partial saturated and at the saturated? Yeah, that's a good question. I think it should be a little bit different, but unfortunately at this time we didn't measure all of the volume for the 3 water content. Yeah.
I'll ask one last question.
Okay.
You took cores down to 30 centimeters, is that correct?
Yes, yes.
And it was tilled to a depth of 20 centimeters?
Yeah, just till 20 centimeters.
Okay. Did you look at the change in thermal properties as a function of soil depth within your data? For example, the soil that's in your bottom core was below the depth of tillage and may have different properties, organic matter content, clay content, than the soil that is being homogenized by tillage.
Yeah. I didn't check the soil thermal properties change with depth. I think we teenage and to connect soil cores with time after subsequent rainfall. We want to get a range of bulk density and water content. So to check the relationship of the soil thermal properties with water content and bulk density. That's our goals. Yeah. So we just want to get the soil cores at different bulk density.
Okay.
Okay.
Well, thank you once again.
Thank you.
Do you know how to get your account?
Yeah.
Okay, welcome for part 2 of the soil seminar.